So I've heard quite a bit of confusion lately as to what are this guy and this guy. Well, first let's just say what they are. This is the Greek letter omega or lowercase omega, and this Greek letter lowercase alpha. But what do they actually mean? What are they? Well, this is angular velocity, and that's angular acceleration. It's great, that's their name, but what do they actually do? Well, I think it's best to do this with an example problem and compare them to regular acceleration and regular velocity. Now, regular acceleration and regular velocity, they have a single direction in a 2D space and a singular magnitude in a 2D space. Singular magnitude, it's not in space, it's just a number. But the velocity here, if something's moving in circular motion, is tangential to the circle, and the acceleration is centripetal or inward because that's where the net force is directed. Now, that's very useful for determining something like the force of friction on a car needs to go around a circular racetrack in order for it to make its turn correctly, but it's not very useful for solving how long it takes for the car to go around that racetrack. So, let's say we have a racetrack, and the car goes a quarter of this racetrack in 30 seconds. What does that mean? That means that the car is going over this distance here, but it's not doing it in a straight line. It's not doing it in two lines like this. It's going over in a curved distance, meaning that we have to use angular velocity and not regular velocity. Because if you try and solve it with regular velocity, you're just going to simply get the wrong numbers. That's not the direction that this is not this. So, just as velocity is equal to the change in position over the change in time, angular velocity is equal to the change in angular position over the change in time. But what's angular position? Well, let's look at this circle, except let's cut it to quarters. So we're just looking at that quarter. It's a 90-degree angle, so it's just that one quarter here that we're looking at that the car went over. So the car's going over this line right here. This line right here, that is our angular displacement. And it's not, notice how it's not one straight line. It's not two lines like that. It's somewhere in the middle along a curved line. And we measure that in radians per some unit of time. Here I'm going to use seconds. So, how do we get the radians? Well, one circle, or 360 degrees, is equal to 2 pi radians. The math for that, that's kind of a prerequisite for this. If you need to do that, I would suggest Googling it. But, so we can find that the circle, or this fourth of the circle, is equal to the 360 over 4, meaning that's equal to this over 4. So 2 pi over 4, which is just the same as multiplying it by 0.25. So that's great. That's our angular displacement. That's the distance that it's gone on this line here in radians. And we have our change in time because we have it right here with this 30 seconds. So our angular velocity for this period over here is 0.25 times 2 pi over 30. And I already solved this, so we get our angular velocity is equal to 0.05 radians per second. So now what can we do with this number? Well, let's expand upon the example a little bit. Let's say that the car keeps going, but it accelerates so that in 10 seconds, it reaches a speed of, or not a speed, sorry, an angular velocity of 0.15 radians per second instead of 0.05 radians per second. So now we have to introduce lowercase alpha, or angular acceleration, into the equation. So just as acceleration is equal to change in velocity over time, angular acceleration is equal to change in angular velocity over time. And we can just solve this very easily, like we would for acceleration. We have our second angular velocity here, and our first one right here. So our change in angular velocity, there we go, is equal to this 0.15 radians per second minus 0.05 radians per second. So we get that equal to 0.15 1 radians per second. We could plug that right back into this equation. To get our angular acceleration is equal to 0.1 radians per second over that 10 seconds. So we get that our angular acceleration is equal to 0.01 radians per second squared. And I seem to have run out of space here. So I'm going to go back over here now. So now we have our 0.01 radians per second squared. Now let's finish the example. Let's say that this car continues accelerating at that acceleration for the remainder of its time on the track. So its angular acceleration is going to equal 0.01 radians per second squared. I'm just using a little r there. It's not radius, it's radians. And now let's say that we want to know how long it takes for the car to complete this whole circle. Well, we know that it goes 30 seconds here, it goes 10 seconds here, but we don't know the time it takes for it to go here. So let's solve for it. We know that this has a constant angular acceleration, meaning that we can bring back the old UAM equations, but this time as uniform angular accelerated motion. If you'll remember, one of our original UAM equations was change in position is equal to initial velocity times change in time plus 1/2 times acceleration times change in time squared. And I had that written on a sheet next to me because I could not have remembered that on my own. Now, here's the thing, is that we don't have this. We don't have this. We don't have this. And we're solving for these two. So what can we do with this equation? Well, instead of using it in this form, we can convert it to our angular position, or change in angular position, is equal to our initial angular velocity, delta t stays the same, plus 1/2 angular acceleration times the change in time squared. Now this we can actually work with. We have 1, 2, 3 of these, and we solve for these two. And 1/2 just stays as 1/2. So now let's solve for it. We know that angular acceleration is equal to 0.01 radians per second squared. So I'm going to start off from the right because I'm feeling like it. Times delta t squared. Now this is plus the initial velocity, the initial angular velocity, which for the purposes of this, we're only going over this half circle here. So we're going to use this as our initial angular velocity. So 0.15 radians, and that's times delta t. So 0.15 delta t. And this is all equal to our change in angular position. Now remember that the whole circle is equal to 2 pi radians, meaning that 2 pi radians to our circle, but we're only using half the circle. So we're just going to divide this by 2, cancel out the 2's, and get pi as the measurement of this displacement in radians. So now that we have this, we can solve for it algebraically, distribute the 1/2, and get pi is equal to 0.15. I'm just going to drop the delta and use t is equal to 0.005 times t squared. Or I'm sorry, I used an equal sign here. I should use a plus sign. Now this right here, we can just reform this into a quadratic equation in the form 0.005 t squared plus 0.15 t plus pi. Now, some may recognize this as quadratic, but some may not, so I'm going to go into it a bit more in depth. A quadratic is just any equation or any function in the form ax plus bx plus c, or as this is our most common form. Sorry, ax squared. This is our most common form for a quadratic that we're going to use here. And it just directly does this. This is our a, t is our x, this is our b, this is our x, and this is our c. It's just values that we're not used to. So if I were to plot this, which I did on Desmos, it would look a little bit something like that. And so we can solve for it using the quadratic formula. So here I'm going to just adjust x to t. So t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, I already solved this, so, and I got t is equal to 14.21 and negative 44.21. Negative 44.21 is our answer over here, and 14.21 is our answer over here. But we can only have one of these solutions, and because we're solving for time, the time for it takes to do this, so I'm not sure if we can have negative time, because unless this thing is going back in time, which unless this car is somehow traveling through time like it's from Back to the Future, I don't think it's doing. So we can just cancel out this answer because it doesn't make sense. Meaning that our time for this half rotation here is 14.21 seconds. So our final time for the total thing, so our net time, oh, that's a really ugly, there we go, is equal to 14.21 plus the 10 seconds plus the 30 seconds. So we eventually get that equal to 54.21 seconds for the car to go around the racetrack. And one thing that you may still be wondering is, well, what direction is the angular velocity in if it's not in a straight line like this is? Well, that's a topic for something completely different. I will link a video to Flipping Physics who describes it better than I could with better visual aids, but it basically gets into 3D space that I can't show on paper. And so over here, we've learned that angular velocity and velocity are not the same thing, and neither are acceleration and angular acceleration. And we've learned how we can solve for a car going around a racetrack. And I want you to try this as an example problem. Try and solve it for a car going around a racetrack that's shaped like this. Now apply any variables you want, or any values you want, but just recognize that all that these two here are, circles. So velocity here will change into angular velocity as it goes over here. So try and solve that on your own. Put an answer in the comments, and I will see if I'll answer it. I don't know. Maybe I won't even look at them. This is the first physics video I'm making. Who knows if I'm even going to make more.